Hello everybody. We continue to study what is related to partial derivative of higher order, and let me give a standard definition. The function f of n variables is called twice differentiable at x naught at a point x naught in Rn if partial derivatives with respect to each variable xi, I from 1 up to n, exist in a neighborhood of x naught and are differentiable at x naught. If all partial derivatives d2f with respect to dxi, dxj, ij from 1 up to n are continuous at x naught, then f is called continuously twice differentiable at x naught. And shorter we can write it like f is in C2 of x naught. In fact, that is not usual. I mean, when we say about such a class C2, we suppose that f belongs to C2 on a set, on a domain. But for a while, let me use this notation as well. In fact, as we know, partial derivatives in general depend on the order, and if we suppose that they are continuous, then we can forget about the order. But in fact, we don't need to do it here, since the supposition of differentiability of the first partial derivatives is also sufficient for independence of mixed derivatives of the order. So maybe I'll do a remark. Theorem 2, independence of mixed partial derivatives on the order is called also Schwarz theorem. Since there is another condition which is called Young theorem. So if partial derivatives are differentiable, at x naught, then second order derivatives at x naught do not depend on the order. The theorem is proved quite analogously to Schwarz theorem, but I'll not do it. And also, let me mention that both conditions are only sufficient conditions. So mixed partial derivatives may be equal without satisfying either of those conditions. And also there are examples when one of conditions from Schwarz or Young is satisfied and another is not satisfied. So all possibilities may happen. But in the future, I plan to suppose more, so just continuously twice differentiable. Because, of course, we need to avoid that irregular case when partial derivatives do depend on the order. That is very strange situation and we avoid it. So now I want to explain how to understand the second differential. So recall, functions of one variable. F is a function of one variable. Then what happens? Then what we can deduce? Then, as we know, second differential is differential of the first differential. And remember, so differential could be written as, okay, let me avoid x naught. as the product of derivative times increment of the argument or differential of the argument. And if x is an independent variable, so it doesn't depend on something, we can choose increment of this variable as we want, what means independent. So we may consider, we may vary the argument as we want. It doesn't depend on anything else. Then what we can do? We can consider dx as a constant, and then second differential is nothing else but the second derivatives times dx squared. Usually we omit those brackets and do not write brackets, so that is standard formula for the second differential. And what is important also here, because look, so when we consider the first differential, we consider the increment of the independent variable x. And then we should take the second differential. So once again, we need to consider an increment of the variable. So we could, in general, what is this differential? It should be differential of f prime of x times dx, and that is, let's say, second derivative of this, first derivative of that times an increment which is in general different from what was at the beginning. So that is would be how to understand this notation without any extra suppositions. But we put extra supposition. We take delta x equals to dx. That is why we obtain this formula. And dx can be considered as a constant. So that is the situation with functions of one variable. Now, for functions of n variables, what we have? Then differential, as we know, is the following expression. Where we took dx1 and so on up to dxn to be increments of independent variables. So we have n independent variables. Each of them has its own increment. Now, in other words, we vary each of variables as we want. And as we know, in fact, this formula is valid in more general situation when x1, so on, xn may be functions. Nevertheless, formula is still okay because of chain rule for n variables. Now, what is about second differential? Okay, formal definition is a little bit similar. So, if f is twice differentiable, then second differential of f is defined as differential of the first differential. So the formula is the same, but of course what is written is not good, because I didn't say where the function f is twice differentiable. So firstly, let me include here at x naught. Then I should put here x naught. And then, okay, I should take differential at x naught. And of course, once again, we need to put extra suppositions, like here, because, but now we have many differentials of variables x1 up to xn, so it means for the second step also we should consider different increments of those variables. So let me write it like that. So here we suppose that increments of independent variables for both differentials are the same. So like for functions of one variable, instead of dx and delta x, we have the same dx in both computations of differentials. So in general, as we know, twice differentiability does not imply that second derivatives, at least we, better to say, I didn't prove that twice differentiability does imply independence of mixed variables. So it means that we proved that if f is continuously twice differentiable, then mixed derivatives do not depend. So it means that now we can find out formulas for second differential. So how to obtain the formula? So suppose f belongs to C2 at x naught, right? And x1 so on up to xn are independent variables. Then we can compute the differential, second differential at x naught. So what is it? We need to differentiate the first differential. So let me write down df over dxn at x naught, dx1 plus so on, plus df over dxn at x naught times dxn. So I need to find differential of that. And in fact, I made a mistake, because here I should consider varying point, but I need to take differential at a fixed point. So I consider differential, the first differentiable, at a variable point, not at x0, but in a neighborhood of x0, and we find differential of this function of x at x0. So since x1 and so xn are independent, that's important, we suppose that each of them is constant, so they do not depend on the point x. It means I can write as follows. I find differential of that function at x0 times dx1 plus so on, plus differential of the last derivative at x0 times dxn. Okay, now we need to find differential of a function of n variables. It means I need to compute all partial derivatives with respect to each variable of that one. So d2f dx1 twice firstly, dx1 plus d2f dx2 dx1 at x0 times dx2 plus so on, plus d2f over dx and dx1 at x0 times dxn times dx1. So that is this term, plus so on. So each of terms in that sum will be computed in an analogous manner. So I will write the last term dx1 dxn at x0 times dx1 plus so on, plus d2f dxn twice at x0 times dxn times dxn. Now, as we know, here we have partial derivative with respect to x and x1, and here inverse order. But as we know, if function is continuously differentiable, then those partial derivatives coincide. And it means that we have two equal terms. And analogously, we can proceed with other mixed derivatives. And if we look at those terms, so you see, okay, maybe I'll write once again in more details firstly, and then we'll discuss how to write it in a more convenient way. So 2 times d2f dx1 dx2 at x0 times dx1 dx2 plus so on, plus 2 times d2f dx1 dxn at x0 times dx1 dxn plus so on, plus d2f over dxn twice at x0 times dxn squared. And after that, we observe that we can write it in a more convenient way using such a formal operation. So I will write d over dx1 times times dx1 plus so on plus d over dxn times dxn squared f at x naught. That is a formal writing, because here you see we have something strange, and in fact there are different understanding of this notation. Here I consider it as operator, and that is the short formula, so let me write it. d2f at x naught equals to d over dx1 dx1 plus so on plus d over dxn dxn squared f at x naught. That is formal writing, and let me show how it works just for two variables, n equals to 2. So here we have a function of two variables, f of x, y. So second differential at a point x naught, y naught should be written as d over dx dx plus d over dy dy squared f at x naught, y naught. And how to understand this writing? So firstly we take square. Just take square of the sum. It gives d2 dx twice dx squared plus 2 times d2 dx dy dx dy plus d2 over dy twice dy squared, right? Then I should understand what to do with this. So what we do? We have an empty place here, and we put our function f on that empty place. And after that, point. What's about point? We put it here. So every time we compute our partial derivative at the same point. So also here, same point x naught, y naught. So once again, how to compute the second differential? You take square of this expression, and then you substitute symbol of the function on empty places and compute those partial derivatives at the point x naught, y naught. And let me also recall that this was the case of independent variables. So now what happens for the case of dependent variables? So if x1 so on xn depend on independent variables, let's say t1 so on up to tm, I don't know how many, then the formula for the second differential will be different. Why? Then f of x1 so on xn can be written as f of x1 of t1 so on up to tm so on xn of t1 so on up to tm. So and I can write it as a composition. So that is a new function which I will denote by h, depending on t1, so on tn. So what is about second differential? So second differential, I'll forget about the point where we compute it to shorten the formula. That is second differential of the function h. Of course, points should be changed. But for the function h, we know the formula. So that is partial derivative with respect to t1, tm dtm squared h. And that is quite different from what we'll obtain if we will compute the differential of the function f. So let me compute it in a different way. So second differential of f is first differential of the first differential. As we know, for the first differential, the formula for the first differential, where is it? Yeah, that one is valid for both cases. I mean, when x1 so on are independent or when they are dependent variables. So let me write the formula for the first differential, which is still okay when we have dependence. But now, when we compute differential, we have differential of the sum. So rules are the same as for one variable. So I can write as differential sum of differentials. Then I will write it like that. Differential of each of derivatives. So differential of product equals to differential of the first times second plus the first term times derivative of, differential of the second. So how to do with differentials? It's the same as we do with derivatives. Right? Okay. Then what we observe? We observe that the first n terms, they are the same as we did here for the case of independent variables, right? So it means for the first terms, the same formula as I wrote before is valid. So squared f, that is the formula for the first terms, and we have extra terms which are not zero in general. dx1 squared plus so on plus df over dxn times dxn squared. So like for the functions of one variable, the formula for the differential of the function of n variable, that is the formula maybe let me call it formula for the second differential of the function of n independent variables. So that formula is valid only for independent variables. And for dependent variables, we have extra terms. And let me give a remark. The formula, let me write it shortly, d2f equals to sum d over dxi squared f is valid also for the case when x1 so on xn are linear functions of independent variables Okay, let's say T1 so on up to Tm. I'll use this remark a little bit later, so it will be quite important. And why this remark is correct? Just because of this formula, right? So this remark was proved by that formula. So if x1 so on xn are linear functions, then second differentials are zeros, because all partial derivatives of second order of functions of several variables are of linear functions are zeros. Okay, so now by induction define differential of mth order to be differential of former order, and f belongs to C m at x naught. So m times continuously differentiable, and if x1 so on xn are independent variables, then differential of mth order at a point x naught can be computed formally as this expression. So we take nth power of this expression and remember how we have to do it. We take formal power of those expressions, and after taking that power, we'll obtain partial derivatives of mth order of what? Of the function f at x naught. So we'll need to substitute symbol f on empty place after taking the power. Okay, now theorem 3 is Taylor formula with remainder in Lagrange form. So if f belongs to Tm plus 1 at a neighborhood of x naught, epsilon greater than 0 x naught in Rn, then for arbitrary x in the neighborhood, there exists a point xi in that neighborhood such that f of x equals to f of x naught plus the first differential at x naught plus second differential over 2 factorial plus so on plus mth differential f at x naught over m factorial plus m plus 1 order differential f at xi over m plus 1 factorial, where dxi are equal to xi minus x naught in formulas star. So let me put it star. So for the differential, here it is not x naught, but the same agreement is applied. I didn't say that x are independent, but of course it should be said as well. Of course, x are independent variables. Yeah. Otherwise, formula star is not true. Okay. So, proof. I'll start with recall Taylor formula for a function capital F of one variable. t, variable t. So what is it? F of t equals to, in fact, not Taylor but Maclaurin formula. I want to write Maclaurin formula. Plus f prime at 0 times t plus so on. Second also. Let me write plus so on plus nth derivative at 0 m factorial t power m plus derivative for the m plus 1 at the point C, m plus 1 factorial t power m plus 1, where C is between t and 0. So that is Taylor formula for functions of one variable. Now, observe that we can rewrite it. How? We can rewrite it as follows. What is written here is precisely formula for differential, I mean without factorial. So if t is independent variable, then we can write it as a differential. So df at 0 plus d2f at 0 over 2 factorial plus so on plus dm capital F at 0 over m factorial plus dm plus 1 f at c over m plus 1 factorial, where dt is taken to be just t. So that is a key observation. We rewrite usual Taylor formula in such an unusual form with the help of differentials. Then what we do? We take a particular case, so put f of t, let it be f of x naught plus t times x minus x naught. So capital F is a composition of two functions. F is a function of n variable, and what is in brackets is a linear function of one variable, or better to say a linear mapping, because you see we have vector. This vector can be represented as, let me write it in details, x1 minus x0 1, so on, x0 nth component plus t times x n minus x naught n. Yeah. So you see, every coordinate is a linear function of t. Is a linear function of t. And now I'll refer to this remark. So the formula for second differential, and also by induction formulas for differential of arbitrary order, are valid also for the case when each coordinate is a linear function of independent variable. So t is supposed to be independent variable. Hence, the formula was written here that is valid formula for the function capital F. And let me write then in details what is differential capital F at t, let's say, because I'll need to substitute later either 0 or c. So at an arbitrary point, differential of kth order of the function f. So as we know, that is derivative of kth order derivative at t times dt. But what is this kth order derivative of capital F? How to compute it? So let me proceed for the first particular cases. So let me start with the first derivative, f prime. What is f prime? By the chain rule for functions of several variables, we'll need to write it as follows. Partial derivative of f with respect to xi at the same point x naught plus t x minus x naught, right, times derivative of this ith variable, like here, with respect to t, and that is precisely xi minus x naught ith coordinate. So let me recall, I didn't write, sorry, that point x naught has coordinates x naught 1, so on, up to x naught n. Okay, then what is analogously, what is about second derivative? We should differentiate this expression. T appears only here, so we apply second time this rule, and it's easy to understand that what we have is that one. Squared f at so I did it once in details, but in a different point, but it doesn't matter, of course, at which point to compute it. So we differentiate that function, and we differentiate it again like we differentiated capital F. And next derivatives will appear. And so on. So we may continue. And as a result, we have kth derivative equals to this expression power k, f at x naught plus t times x minus x naught. And yeah, it gives, I'll not multiply it by dt power k, by the way, dt power k, dt power k. I'll not multiply it. Now, look, so let me understand what we'll obtain for as a result. So let us substitute. So substitute substitute dt equals to t equals to 1. Substitute here in this formula. So what do we obtain? Capital F of 1. And what is capital F of 1? If we substitute t equals to 1, we have just f of x. That is f of x equals to capital F at 0. If we substitute t equals to 0, we have x naught here. So f at x naught plus then first differential. So what is df at 0? Let me write in details. So that is first derivative at 0 times dt, and we took dt to be 1. So f prime at 0, f prime at 0 is precisely, that is df at x naught when we accept to be dxi equals to xi minus x naught I, by the way. Yeah, here I forget coordinate I. Coordinate I. Okay. You see, xi minus x naught I here. Analogously, second differential at 0, double prime at 0 dt squared, dt equals to 1. So the result is second differential at x naught, and so on. So I can continue up to m order differential. Then new element is about the point C. What happens for differential of order m plus 1? So that is derivative of order m plus 1 at c times dt power m plus 1. dt is 1. And it means I need to write differential of order m plus 1 of f at a point x naught plus c times x minus x naught. And you see now, where is c? C is between 0 and t, which is equal to 1 in our case. I substituted t equals to 1. And if t is between 0 and 1, then psi, which is x naught plus t times x minus x naught, is a point somewhere on the interval which connects x naught and x. And if x is a point of our neighborhood, then psi will be also a point in our neighborhood. So the last term is precisely as we want. And theorem is proved. Theorem is proved. Corollary. Taylor formula. with the remainder in piano form. If f belongs to Cm in a neighborhood, then we can write f of x equals to f at x naught plus df at x naught plus d2f at x naught over 2 factorial plus so on plus dmf at x naught over m factorial plus little o of x minus x naught power m as x tends to x naught, where dxi are written xi minus x naught I from 1 up to n in the differentials. Yeah, once again, this formula for x naught should be also added here. And also here, x naught is x1 naught, x naught 1, x naught, and for completeness should be added, of course. Yeah. Okay, proof of this corollary. So what we have to do, we apply the theorem. So by theorem 3, we can write f of x equals to f at x naught plus df at x naught plus second differential over 2 factorial plus so on plus differential for the m minus 1. We can stop only here, not further. And now differential for the m at the point xi, m factorial, with the same agreement about differentials, and xi is, in fact, as we know, is between x naught and x. So I should apply not only the theorem itself, but also the proof of the theorem, namely that the point xi is between x naught and x. Okay. Then what happens if x tends to x naught? Then we can write so you see what is difference between those two formulas. We need to prove that our m's differential at the point xi divided by m factorial is equal to m's differential of f at x naught over m factorial plus little o of this term. That is what we need to prove as x tends to x naught. And how to proceed here? We write the difference between two differentials. So differential at xi minus differential at 0. Oh, sorry, at x naught. At x naught. So what is it? As we know, there is the following expression. So 1 over m factorial times sum I from 1 up to n d over dxi times xi minus x naught ith coordinate power m, and I should write it at point xi and at the point x naught. So how to understand this writing? Firstly, we take power of this expression, and after obtaining the result, what we should do, we should substitute here f and take it firstly at the point xi, then at the point x naught, and consider the difference between the values. So now look what we have. Okay, how to... Let me consider just one term as an example. So I can write it explicitly using so-called polynomial formula. I'm not sure if you know it. Mth power of a sum of n variables. So what is it? That is the sum for all indices such that k1 plus so on plus kn equals to m, and we have m factorial is cancelled, 1 over k1 factorial, so on kn factorial. And then partial derivative of mth order with respect to x1 k1 times, so on xn kn times f at the point xi minus partial derivative f with respect to xn kn times at the point x naught times x1 minus x naught 1 k1 times, so on xn minus x naught n's coordinate kn times. Yeah, the sum is taken over all combinations of k1 so on up to kn, non-negative integers, non-negative integers such that the sum is equal to m. That is explicit formula for that expression. And then look what happens. Because of continuity of that partial derivative, this tends to 0 as x tends to x naught. And if we divide this expression, so let me write this expression divide that expression over length of vector x minus x naught power m, then that is less or equal than 1. Why? Because for every coordinate we have the sum of powers equals to precisely m, so number of multipliers is the same as here, and for each one multiplier we have x I minus x naught I over the length is less or equal to 1. We applied it several times. That is how to prove the result. So we have finitely many terms, and each term is a product of something bounded after division by x minus x naught power m. So we divide by this, then this term is bounded, that term tends to 0, so we have finitely many terms, little o of x minus x naught power m. Okay, the theorem is proved, and let me make a remark about second differential, one more remark. So second differential of x naught at the point x naught, which can be represented also as sum ij from 1 up to n, second derivative of f with respect to xi, xj, and the point x naught times dxi, dxj. That is quadratic form with respect to the variables dx1 so on up to dxn. I hope you considered quadratic forms in linear algebra, since I'll use a little bit theorem of quadratic forms in future, in next future, in fact, yeah. And also I used here so-called polynomial formula, that is a generalization of binomial formula. So polynomial formula a1 plus so on plus an power m equals to sum over all non-negative integers k1 up to kn, m factorial over k1 factorial so on kn factorial times a1 power k1 so on an power kn. That is polynomial formula. If n equals to 2, you will recognize immediately binomial formula, because k1 plus k2 equals to m, gives precisely m factorial over k1 factorial m minus k1 factorial. So binomial formula is a particular case. And yeah, I have no time to prove the polynomial formula. You may refer to combinatorial considerations. It looks like a combinatorial formula. You have m brackets of this form. M brackets of that form, right? M brackets. M brackets. And then you take one term from each of those brackets. All terms have such a form, and if you obtain such a form of final product, then you should compute how many such terms you have, and that is precisely how many terms you obtain. That is a sketch of combinatorial proof of that formula. Okay, so then I think that's all what I wanted to say. Just a moment, maybe a few words. Yeah, of course, suppositions here about m plus 1 times continuously differentiability, and here for corollary m times continuous differentiability, not strong suppositions, of course. Formulas are valid for essentially weaker suppositions on the function f, but I'll not give the detailed proofs, although they're approximately similar. Okay, that's all for today. Thanks for your attention. No questions? Bye-bye.